here. Colin. Matt Thompson. Jordan. Jack. Ray. Alex. You. And the other. Jack. So good. So these are out of 20 points. Some of you got some bonus points for doing parts of the other questions. Just generally, people did quite well. The solutions are posted. So if a little point was taken off or a comment was made there, you can find more detail by looking at the solutions that are there. If you have any questions after looking at that or going back over the material, parts of those, or what was going on, or problem, or even if you got the points for the problem, because I was a little shaky about the reasoning for this and wanted to understand it better, you would find to talk about those in office hours or an email for further clarification. There were some practice problems given out as well, and I'll do that from time to time. So as you're studying, if you go back over those, particularly as we get ready for the first exam in a few weeks. I think that's maybe after the 4th homework or something like that. Then, yeah, so there's other material to study. Okay? Today we want to talk about independent events. Generally, the probability of two things together can be written as the probability of one of them happens times the conditional probability, the probability that the second one happened given the first, either as probability of A times probability of B given that A has happened, or viewing it the other way, the probability of that whatever B is times the conditional probability of the other one. But if they're independent, the conditional probabilities simplify. So that the probability of A given that B has happened, generally we write this as probability of A intersection B over the probability of the thing we're conditioning on or the thing that we're given. And if this simplifies according to this definition, then one of these probabilities cancel, and we're just given the probability of A. So if B has happened, it doesn't change our chances of A at all, and it's just going to be the same. You would get the same type of simplification, conditioning on A, asking questions about B. A won't matter, won't change our assessment of the probabilities. If it's something totally unrelated, it's like asking, what's the chance that it's going to rain today, given that they're playing a certain song on the radio? Well, most likely that doesn't have anything to do with it, right? Unless they pick songs that are related to the weather and on some station or other, but more like it's not like something like the cloud cover or the the humidity or something else that would more directly affect it, right? So this comes up in a number of circumstances. If we have a series of events or we repeat something and it doesn't change the chances. So let's say the simplest one of these is we roll, say, 2 dice, and we ask something, what's the probability that the first one is greater than 3, and the second one is greater than 4. And let's say these are 6-sided dice. If there's no interaction between these two things and they're independent of one another, it's very reasonable to say that the probability that both of these things happen is just the product of those two probabilities. And so greater than 3 would be 3 out of 6. All those outcomes are equally likely. If they're fair dice, would generally mean that it's 1/6 for each number. Greater than 4, there's 2 ways that happens. So this would be 6 out of 36, or just one out of 30, 1 out of 6, or something like that. Well, a few other applications that are a little more interesting. You're testing individuals. Say, any questions about that? So, as an example, you have 3 people that are unrelated to one another, and you're asking what's the chance that their infection, that they have a disease. Right? Let's say the disease has a prevalence in the population of 1%. And these 3 people, the chance that one person has the disease doesn't affect the other person's chance of having the disease. So that's kind of, that would be an important assumption if these are contagious diseases, or it's people that are in groups, or genetically related diseases, right? So it's 3 different people, they're not in a contagious situation. Then you could say, what's the probability that at least 2 have the disease? We could look at something like that. If they're independent, well, for this random variable, for this outcomes of these 3 people, we could look at all different possibilities. That person 1, person 1, and event of B is going to be a person 2, and C is going to be a person 3, and they can have different outcomes. One scenario would be that they would all 3 have the disease, so the Y there is that they have the disease. If they're independent, right, then the probability of these 3 things is just going to be the product of the probabilities. It works with 2 events, it would work with 3 or multiple larger things as well. So probability that's yes for the first person, yes for the second person, and yes for the third. And if these are all 0.01, right, that to the cube, 0.000001. So quite unlikely that you get 3 independent people all having a somewhat rare condition. Right? But another way this could happen and still have at least 2 is you can have the first 2 have it and the third person doesn't. If these are independent and the chance that one person has it doesn't affect the others through some contagious mechanism or something, the chance that you would have this particular pattern in these 3 people, right, is just the product of those probabilities. So the probability of yes for the disease, yes for the second person, and then a no. So it's 1% for these 2 that are yeses. Right? The probability that the person does not have the disease is 1 minus that. Minus 0.99, so it's going to be 0.000099. Still small, but a lot bigger than all yeses. how many other ways can we have at least have exactly two people? Get the other combination. Yes, no, yes. Or no, yes, and yes. What's the probability that the first person has it, the second person doesn't, and then the third person does again? And it's going to be the same probability, right, as that other one. 0.01, 0.99, 0.0009. Going again, and same thing for this one. No, yes, yes, it's going to give us the same probabilities here. So if you add up those four scenarios, you get a probability that at least two people out of the three that you test or study have that disease. So independent events are useful like that. Any questions about these type of calculations? So a disjoint event or mutually exclusive ones are ones that right, they have no outcomes in common. And so if things are mutually exclusive, are they independent of one another? So if things are disjoint, would be things that just don't have any outcomes in common. So in a Venn diagram, the usual situation is A and B, they have some type of overlap. But if they're this mutually exclusive disjoint, they have to be drawn so that there's no overlap between these things. And what happens in this scenario over here, probability of A and B, does it equal the probability of A times the probability of B? Could you take the probability of the circle A there times the probability of B there and multiply them and get the probability of some type of intersection? No, you don't actually get this. If they're disjoint events, if they're mutually exclusive, they have nothing in common. So the probability of A intersection B in that type of scenario is just 0. And as long as A and B have some probability or possibility of happening, they won't be possible. Let's look at the handout a little bit for some more examples. So the handout today begins really with this first example. So if you have a disease has a prevalence of 1% in the population, and you're going to pick, say, 20 people, what's the chance that at least one of these people have the disease? Is that probability that at least one of the 20 is going to have the disease? Is that more than 50%, or how high is it? If the disease is independent across different people, we can try to answer these problems. But first, it's easier to consider the 3 people, assuming they're independent. The probability that, yes, that somebody has the disease is 1%, so the chance they do not have it is 99%, 1 minus that. And if we want to ask the question, what's the probability that at least one out of these 3 have it? Right? Any of these questions that are faced as at least or less than is often worth considering, maybe calculating the other direction, like 1 minus the probability of the opposite. So at least one is the opposite of that is nobody has it. So 1 minus the probability of these three no's. Right? And the chance that nobody has it is no on the first one times no on the second one times no on the third. So 0.99 for each, so 0.99 cubed. And that ends up being about 3%. We can do it a little more accurately in the next page is this table. Right? We can actually, for 3 people, right, write out all 8 possibilities. Yes or no for each one, 2 choices for each, 2 times 2 times 2 gives 8 possibilities. The probability of, but nobody, all of them have it was this one. And then we looked at a couple of these others where 2 of them have it. The chance that, the probability that one person has it, well, there's 3 distinct ways that people can have, we can have one person have it. We can have the first person only having it, or the second person only having it, or the third person only having it. These three things are disjoint. There's no intersection between them, as it's phrased. So the first person only having it is in this row. The second person only having it is in this row. And the third person only having it would be in that row. So the chance that exactly one person has it is we have sort of all the same probabilities by there's 3 of them, so 0.009801. So we get a probability of one of these. There's a 3, 0, 24. Carry to the 27, 29. Right. About 3% of the time, we'll have exactly one person. The chance for 2 people are quite small, or 3 people. So the probability of no one is about 3% in there. If you add up those other 7. But if we asked about 20, right, then we can still do some of these problems. Right? So we can look at, say, something like 20 people. What's the probability? At least one person out of 20 people that come in and test for something, for a rare condition, a 1% condition anyway. Right? What's that? 1 minus the probability of none is what we want. And assuming these people are independent, the probability of none is, no's for all of them. Right? And so that's 0.99 for each one. That raised to the 20th power, and once subtract 20th power is 0.8179. Eventually, the 0.99s that are less than 1 start making that smaller. There wasn't, maybe go down more than 1, 0.01 at a time. And so subtracting, we get about 18%. So the chance that you would get at least 1 positive would be 18%. So if you needed to test blood samples, right, and had a large population that you're studying, and there's a condition that affects about 1%. Right? What could you do, to save on testing costs? Right? So assuming you could get valid tests by combining samples together or portions of samples together, right? One scenario, right? The probability of 20 no's was about 0.82 approximately. So the probability of at least 1, which is 18%. So if you tested, say, 20 separately, then you get 20 tests. For certain. An alternate way that this type of information can be used you group them together, you group them all together, let me write that over here. If you group all the samples together, assuming you've taken enough blood to maybe test some samples twice, right? You group them together, and then there could be no positive tests, and maybe it would take at least one positive. The chance that no positive tests are detected by just doing one kind of conglomerate test, 82%, and then 18%. There's at least one positive. And then, so if there's no positive, testing them all, you're done. You've done one test. If you had at least one positive in there, right, then you could say, assume you've saved enough blood or whatever you're testing, test all 20. Find the one or the few that are positive. In this case, you've done 21 tests overall, assuming it costs the same. But on average, using this procedure for every group of 20 people, how many tests are we going to do? What would be kind of the expected number of tests we would end up doing in these two scenarios? So about 18% of the time, we only have to do one. 18% of the time, we have to do 21, which is a little bit more than just doing 20. But 82% times 1 and 18% times 21, so that's 0.82. And this one is, what is that, multiplied out, so 816 and 21, so 873, so 378, like 3.78. So on average, we would be doing 0, 6, about 4.6 tests as kind of on average for each group of people. So if they were independent and the tests were valid by combining samples, and you had the authorization to, facilities for doing that, if you could test in batches instead of just individuals, on average, you potentially could do a whole lot less tests, right? Instead of 20, you just go to testing them all separately versus doing testing a batch. And if that's positive, then testing them all. But taking the results if there's 0 positives. So you could potentially save quite a lot. So anyway, independent events, right, get us some ways to calculate different outcomes. Right? But any questions about
Yeah, I have a question.
Yeah.
Let's say for the group where you get at least one positive,
Yeah.
If you were to split that in half and then test one of those halves, would the split still be 0.82 and 0.18 for getting
So let's say you had you tested them all, and there's at least one, you tested, there's at least one positive, right? Then if you split it into, say, 10 and 10, right, and test it, it's going to be, you're going to have to determine those probabilities again, right? So we could make this a little more elaborate, where we test all 20, and we get, 0 positive. Happens 82% of the time, right? That was 1 minus the chance that they're, or that they're all negative, right? 0.99 to the 20th was this calculation. And then the opposite of that is at least 1 positive. So that happens 18% of the time. Now it could be here and say, okay, we've got at least 1 positive. Assume you have enough sample that you could do this again. You could take 20 of those and randomly take 10. Right? So you could kind of split it into 10 and 10, and then test them. And in this group of 10, you might get 0 positive, or at least 1. At least 1. And in these 10, you might get 0 positive, at least 1. Now the probability you would get 0 on this half, now there's at least 1 in there, so maybe it's a little more complicated to calculate. You have to have at least 1 in at least one of these two places. So it's a little bit more complicated to calculate this probability. So there's going to be some probability here and some probability here that's 1 minus that. But we have at least 1. So I was going to say, if you just were testing 10 instead of 20, and if you tested 10 back here, the chance of 0 out of 10 was 0.99 to the 10th. It becomes a little bit more complicated to do that splitting, because if you've gone down here, you know there's at least 1 positive. So 1 has to go here or there. So it can't be just 0.99 to the 10th and 0.99 to the 10th. That wouldn't be using the fact that at least 1 is positive. We will, these probabilities, so this is not what it is, but it's still going to be a pretty big number. We will do a distribution soon called hypergeometric. It's kind of like that capture-recapture problem that we did for the homework. Because once you've found some in here, you don't know exactly if is it 1, is it 2, is it all 20 that are positive, right? So there's a little bit more complication there. But if this was a big pool and then you could split it, you might do another test, and you might weed out another 10 and get that average number of tests down a little bit further. That gets a little more complicated because you have to pool them and then get the results, and then pool them again and get the results, and then maybe test 10 individual ones. But in principle, you might be able to do something like that. Okay. Another type of, so anyway, that's this type of problem. There's other forms of independence that are sometimes interesting to use, right? Sometimes there's given some information, or within a group, different factors are independent of one another. And that's called conditional independence. So instead of things just being independent overall, given a group status, things might be independent. So if you had 2 events, A and B, and within groups, they're called conditionally independent if the probability of A and B, given a group, is the product of 2 conditional probabilities. Or if you have 3 factors, it would look like that. Right? So one example where this is used is in an article on testing of infants, right? And so in this, the A, B, and C are different factors. Are the infants, for studying personality traits in infants, it's harder to do a battery of questions about asking them, do they like to interact with people, how do they feel socially, and things like that. Instead, for very small infants, they researchers in psychology put them in rooms, right? That safe, and then expose them to different situations. Maybe a new toy, maybe a new person, new sounds, and see what they do. Right? Some infants will cry a lot, and others will not cry so much. Others will put some new thing there. It will go over there and get it. Others will stand and stay back and look at it. Right? So some have higher motor activity or lower motor activity, lower crying or higher crying, or some type of fear response, like they'll try to get away or avoid things or just be apprehensive, right, about it. And some research, so this is coming from an article what's on, it's not on there. Right? Let's see if this is on our, that's there. I must put it back over here. Is it in here? Or I can get into there. It's section 5. No, that's not there. It's that's where we are today. Let's see. Where this is kind of disappeared. Here it is. I put it in the wrong place. Right. So this is a research article. Individuals I worked with in the past about studying infants, right? And so the hypothesis, here's the data that they had, different individuals measuring how fearful that we are in response to different things, right? And so there's 3 different variables that define these groups. And the research question groups here was, you know, are there different classes? Are there individuals who are kind of geared to a quick response to stimuli, and others that are more geared to a lower stop? Is there kind of a cutoff? Is, instead of being more of a continuum, are there kind of distinct types that develop over time? And so in this research, they made these, they looked for these groups assuming a conditional independence structure. So let me go to my little thing here, right? So if these things are, they have, there's levels of, let's see, no, motor activity, crying, and fear among, let's see if I have this written out. My notes a little bit better for where that. Oh, I see, it's only 10, that's what it is. Confuse myself. There we go. Given, say, the low activity group is described in this research as the response to the motor, response to the crying level, times response to the fear level, in that group. So if in the group there's a low activation group, a high activation group, and these are both about 50% of the population or 50% of the sample, right? The motor response had a low or high category, right? And in the low activation group, they tend to have lower motor response, the low versus high. But in the higher activation group, the probabilities of getting the lower or high response is like that. The cry variable also was reported as 2 levels. And say it like this, 70, this is how it splits in the low activation group, but it's kind of reversed in the high activation group. And his fear response was something like this, split within the low activation group or this. Right? Now, let's say you observe an infant that has low, so that has, let's see, this is, right, it has high levels of all 3 categories, M, C, and the fear response. So in this laboratory setting where the children are interacting with different experiences, they actually videotape children in these different scenarios and go through and categorize how they're responding to things. Let's say they have the high level of this, all of these things. What is the probability that they're in the low category of these different, up here in terms of their personality type? So low in terms of low activation. So this is really asking what's the chance that they're in that low group given that they have those three responses there. What's the chance they should be classified that given these probabilities? Do these probabilities make much of a difference, really? So things aren't stated in terms of probabilities this direction. The probabilities that they see in the laboratory aren't, or they calculate and report in the articles aren't the other direction. Right, so what they report instead is the probability that they're in this low group is 0.5, and the probability they're in the high level group is 0.5. And the probability of, that one, given the low group, was 0.8. The probability of the higher, that response of this group that they saw was 0.7, and the probability of this one, the low group, was 0.75. So this conditional independence said if we have these three things conditional on this group, is we can multiply these three things together, and so we get 0.8, 0.7, 0.75. But suppose this person had been in this infant had been actually coming from the high group. The probability of these three things, given that they were in this high activation group, would be written assuming they're independent within groups, right? Different levels than the high group, but independent within those. The probability of this level of M given the high one, this level of C given the high one, the probability of the sphere given the high one, and these three things were 30%, 30%, and 10%. So that's 0.009 over here. Whereas if you multiply these three things together, it's about 0.42. So overall, the chance of having this response, whether you're in the low group or high group, unconditional on which group you're in. So out of the entire population, what one is having this, what percent of the sample is having this particular response? Well, there's 42% coming from the low group, which is about half the population. And then a much less common response among this group. And so the average of these two things is about half of 0.429. Half of that is this 0.2145. So about 20% overall have that. So what's the probability you're in this low group, given that you have this? Well, Bayes' theorem says to reverse these things times the probability of the low one over the probability of this category. So we've done this calculation under this conditional independence assumption. So that was 42%, and half the subjects are in the low one. Overall, 0.2145 is the number down here, and half of 42% is about 21%. So 21 over 2145 is about 98%. Which gives us that if an infant had those three responses that are more common among the low activation group, we would calculate a very high probability that they actually came from that group that's under there. So this has been a little bit of an involved example. So, but to connect it to what we've done before is kind of the low-high responses. And then there really are 8 different levels that you can have depending on the combinations of M, C, and F. You might have the lower form of M, or down here where they're all, there's really 8 levels of these 2x2 responses in there. And instead of calculating all 8 probabilities and giving all 8 of those groups, this conditioning, this conditional independence, is that we really figured these things out just knowing 3 things: the probability of M, C, and F, and then multiplying together. So anyway, so we sometimes use independence. Some things are more conditionally independent, and it's just a little bit different in there. In those, so anyway, that's a little bit more extended example of how these things get used in some, at least one problem. Any questions about that? It might be a little, seems like a little confusing to put together, but anyway, it's kind of a way of calculating using Bayes' theorem. A little bit more complicated examples. I think it's kind of maybe interesting that it can handle these more complicated things. So, this general idea of conditioning or splitting data becomes really quite important in actual practical statistical analysis and estimation of probabilities, right? And interpretation of what they mean in practice. So here's one example of this. It's an example of what's called Simpson paradox. It's not a Simpson that was used, not just mathematical results, but a mathematician probabilist in the 1950s described this phenomenon. Here's one example that has been used over time as an example of interpretation of it. Okay. So in this was 1973. This is some data on numbers for individuals who applied to graduate programs at UC Berkeley. Right? At that time, in 1973, men were applying at a higher rate, so about 8,442 men applied to the graduate programs there, and 44% were admitted. Women applied at 4,321, but the admission rate was only 35%, so it was a lower admission rate. Right? And so at kind of face value, does it appear that things are fair in terms of admission, or that there's possibly a bias or a different treatment based on gender? So certainly the rate is lower, right? The idea of conditioning and looking at other factors is possibly by splitting the data by another variable, right, by some other factor. It might be called a lurking variable, a variable that might impact the relationship if things might be changed. Right? So in this example, individuals don't just apply to admission to the entire university. They really apply to different departments. And so here are letters that stand for different departments, or they might be art, or business, or political science, or physical sciences of some sort. So just a whole variety of different things. These are the number of men that are admitted, and these are that apply, and these are the number of women that apply to those different departments. And these are the percent of the men that are admitted to these separate departments, and the percent of women that are admitted to these separate departments. Right? So when things are broken out by this other variable, when it's conditioned on which department people are applying to, does it look like there is the same level of bias as before? How does that happen? So what is happening, right? So kind of reverse changing things, changing the relationships. Right? So what's happening with this condition? Do men and women apply to the departments at the same rates? Right. Some departments, more women are applying to, others, men are applying to more, right? So here, men are much more likely to apply to this one and this one, but a few of these others are much more equal, or more women are applying to some. Right? And this is 1973, so we're almost 50 years later, so some fields that might have been really imbalanced before are not necessarily so imbalanced now, although I don't know what these departments actually are. Do all the departments admit at the same rate? Now, there's a few departments that are admitting over 50%. There's some kind of in the 30%, and at least one that's really quite low, 6-7%. Right? They're getting a lot of applicants, but it's very selective. So men and women are applying to departments at different rates, and certain departments admit at different rates. So, right, if women are applying to departments that have lower admission rates, but men tend to apply to ones that have higher admission rates, things could be exactly equal, but when you aggregate it up, the admission rate for the women could look lower. Right? So that could be part of the story. Certainly that's not the story in these numbers, right? That might not be the whole story about what's going on. Right? But the where women tended to be majority applicants, the admission rates for both men and women were a little bit lower. And these couple of departments where men tended to be the vast majority of applicants, the admission rates were higher. So whatever they are and whatever factors caused those choices, that's a different issue with society and preferences. But it's an example where this effect by conditioning, probabilities can change substantially. The other place that this gets used in some type of examples is in things like rating hospitals or evaluating programs and things. So let's say we have a procedure that is not too uncommon and generally has a high success rate, that there's some risk. And we have two hospitals. Hospital A, 2,100 people come to it, and Hospital B, 800 people come to that one. And some people go through the procedure and die, so 63 out of the 2,100 die in Hospital A, but 16 out of 800 die in Hospital B. Right? Which hospital, given this information, do you think you would want to go to? If you had to choose one. You should choose the one with the higher survival rate, the less death. Will you choose B? Because it has the kind of better performance. There's not a big difference between 2 versus 3%, right? I mean, it's not like 2 versus 20% or something. It's not that big. But there's a subtle difference, right? What other factors might be relevant in looking at hospitals?
Types of people they take in.
It's the type of people they take in, right? If Hospital A is getting, well, the next slide is exactly that, right? So say some people might come in a relatively good condition. They might be younger, healthier, less severe form of early diagnosis rather than later diagnosis for some things. So generally prognosis looks good. Other people who come in a poor condition, maybe they're elderly, frail, or have some other comorbidity. Maybe they have heart disease as well. So there's more problems, right? And so we could have a situation where Hospital A, out of its 2,100 people, it gets 600 that come to it in good condition, and they could achieve a 1%, 99% survival rate for those. And Hospital A could get in the 1,500 who come in the poor condition and have about a 3.8%, right? They started out not so well, so they don't survive as well. But Hospital B, right, might have a different split with 600 coming from this good condition, only 200 here that come in severe cases. Right? And if they achieved if they had a death rate of 1.3% and 4% here, right, the numbers would add up to get that other table. Right? In that other table, when it was aggregated, hospital B had the better survival rate. Right? What's happened in these two once we split it on that extra variable? Then hospital A is lower. In this case, it's lower in this case as well. So whichever type of patient you are, it would look like hospital A would be better. But if you didn't know that information, right, hospital B as an aggregate. So when things like U.S. News and World Report or other things rate hospitals or programs, they usually try to adjust for the mix of patients that are coming in. So if you're in an area where you have a lot of elderly patients, or you have a poor population that generally has many different health issues related to poverty and diet and some other things, if they're getting a mix of patients that's worse, and they have a worse survival rate or longer time in the hospital, you want to adjust for that when you're really rating them. Right? Some large hospitals that are research university hospitals, might have all these specialties. Might have burn units, advanced cancer units, and neonatal intensive care units. So they're getting a lot of hard cases that wouldn't be handled at small suburban hospitals without all the specialty units. Well, that impacts their performance, but if you had the variables describing the patients, maybe you could adjust and make a more fair comparison. So the conditioning and probability gets used, really makes a difference in how you assess things. Right? So, but any questions about that? About the conditioning? Okay. So we're going to do the new topic. All right. The probabilities are also represented as odds, and a couple of them particularly useful in medical applications, right, and public health applications. So if probabilities of an event A are between 0 and 1, right, the odds for an event A is reported as the probability that A happens over the probability that it doesn't happen. If you're given the odds, a number that's an odds, well, what's the range of values that are possible for odds? What's the smallest it can be and what's the biggest it can be?
0 to 1.
Well, it could be 0. If A goes down to nearly 0, this can be 0. If A goes to 0, then this is going up towards 1. So you're getting something basically 0 over 1 is that. But what happens if A becomes really large, almost certain? Yeah, it can go towards infinity. So very large probabilities like 0.99, you have 0.99 over 0.01, and you get an odds of 99 to 1. Calculated as 99 is usually read as 99 to 1 as an extreme, right? So it goes on the positive line. You can invert this, and if you have the odds, if you have the odds of A, the 1 plus the odds of A, if you put the formula for the odds there in there, you end up getting the probability back, so there's a way to convert, right? Just as some examples, if the probability of an event, say, is 1/3, right, the odds of A then are 1/3 right, over 2/3, or the odds of 1/2, right, 1 to 2, 1 for it, 2 against it, right, is how it's often read. Probability of 1/2, then the odds are going to be exactly 1, right? Even 1 to 1. You had, say, 3/4 as a probability. You'd have 3/4 over 1/4, right? And then the odds would be 3. And might be stated as, 3 to 1. 3/4 for, 1/4 against, and so in the betting odds type of thing, you get that. Odds often can be taken from a table. So imagine we have some, say some people that say smokers and non-smokers. This could be called some type of exposure to a disease or contamination or condition, some type of situation, no exposure in other contexts, and then some type of disease. D, bar, no disease. Might be emphysema, lung cancer, or something like that. And say you had 100 individuals of each. Maybe 20 out of the 100 of that group would have the disease or the infection, right? But if it's really tied to the smoking, it could be really rare in the general population. So we could look at the odds of disease given your status. So what's the odds? The odds for the disease among those that have exposure, the smokers. So we want the probability of disease among the smokers divided by the probability of those that do not have the disease. So this is exposure, E, smoke, more neatly. So the probability of disease, right, is 20 out of 100. The probability of no disease in this group is 80 out of 100, which is 20 over 80, or 1 out of 4. What's the odds for the disease among those who are not exposed? So non-smokers. Pretty easy to directly calculate from the table, right? So 1 out of 100, 99 out of 100, or 1 out of 99. So the odds of disease are much higher among those, right? The odds of disease are still less than, 1. The probability is much less than 1/2. The odds are greatly elevated. So that's often captured in what's called an odds ratio. So this is the ratio for disease in the exposed versus in the unexposed. So it's going to be the odds of disease among those who are exposed divided by the odds of disease among those that are not exposed. So the ratio of these odds provides kind of a relative size of the probabilities under these two scenarios. So in this case, the odds were 1 out of 4, 20 out of 20 versus 80 in the individuals who had exposure, but it was 1 out of 99 for those that are not exposed. So this becomes 99 out of 4. Or almost 24.75 right, times. The odds are 24, almost 25 times as high for disease among the smokers versus the non-smokers. So odds ratios gets used as that comparison. If if two variables are independent of one another, what's the odds ratio? So if independent of one another, what can we say about some of these terms in probability? So if they're independent, the probability of D and E is the product of these two things. That's one thing we can say. The probability of disease, given that you're exposed, it's independent. There's really no impact on these. It's just the probability of disease. Whether you're exposed to something, hair coloring, or taking some type of vitamin, if that really does nothing to that particular thing, then it's independent. But it's also the case that the probability of D given, if you're not exposed, should have the same probability, right? It doesn't matter whether you're exposed or not, it's still the same probability. And the probability that you do not have the disease also doesn't depend on the exposure, right? So it doesn't depend on the exposure either. So all these things are just, they're the same. The disease and not disease are one minus each other, and they're all the same. So if we have the odds for the disease among those that have the exposure, it's the probability of D given E. Over the probability you don't have the disease given E. So that, just in general, is the probability of disease over the probability of no disease. It doesn't depend on that. There's some rate of disease in the population, 1% or something. The odds for disease among those that are not exposed, how would that compare? Are the odds going to be any different if these things are independent of one another? So it would be the probability of disease among not exposed, but those things don't, if it's independent, they don't depend. So it's still just the probability of disease over the probability of not disease. No change. Right? So the odds ratio for disease in the exposure versus the not exposure is the ratio of these two things. But if the exposure doesn't make any difference, this is the definition of this odds ratio of D versus the two groups. But if it's the same, right, then it's just going to get an odds of 1, an odds ratio of 1. Right? So the odds of the disease, the chances of it, don't change as you're moving between the different exposure categories. So often in medical studies, things get reported in terms of estimating odds ratios. Let's go back one, the odds ratio, the ratio of odds, what are so probability is between 0 and 1. Right? The odds are between 0 and infinity, because you divide it by something that, 1 minus the probability, that might become quite close to 0. What are the ratios, what are the ranges that are possible for an odds ratio? You're taking odds of one thing over the odds of something else. Right? So you take one of these odds versus the other odds, right? It's two positive numbers, so you can still get down to 0. Right? It's basically 0 under the other of one case, and then the odds is some positive number. It can basically be 0. But you could have the odds be extremely higher under one condition than the other. You can also get up there. One thing that's often reported is the log of the odds ratio index. Now, if you take the log of an odds ratio, right, where's that going to go? If you have something between 0 and infinity and take the log of it, you might get something that's negative infinity between infinity. So, in a lot of medical studies, the odds ratios get reported. So anyway, odds are something that we might see with something that you get out of the probabilities. In some fields, things are reported that way. We'll do a couple other terminology things just to do. Let's do a new example. We won't always do medical examples, but we're doing more of them today. So let's say, so that this prostate cancer, one diagnostic test, the PSA test, is protein prostate-specific antibody test, and in that test, the PSA levels are elevated, and so PSA levels less than 4. Let's say you had 900 individuals. There's prostate cancer is one of these cancers that tends to show up in older men, so men that are 80 or 90, many of them might actually have prostate cancer, but it's also a very slow-growing cancer in most cases. So that after 70, 80, 90, men might have it, or indications of it, but it won't necessarily be the thing that kills them. Just being old and everything else that goes along with that is often much more fatal than that. It's early cases that hopefully are detected early are the ones that cause death earlier. So out of 900 of elderly men, you might have 135 with prostate cancer or indications of it, and 765 that don't. However, if you have PSA levels that are elevated, and it's more rare, right? And maybe it's 20 and 60, and if PSA levels are really elevated, which happens less often, is you might have more of an even split, so 165 and 815. 835, sorry, 835 for if you had 1,000 people. So sensitivity, there's two terms. Sensitivity is a probability of testing positive if you're really positive. That you have a test, a positive test if you're truly positive. So we have a couple ways of deciding a test. So you measure PSA level. Let's say a positive test is that a PSA level is greater than 10. And the true positive in this case is that the individual actually has prostate cancer. So in this sample, right, if we're using this table to calculate probabilities, what's the probability there that you have what's the sensitivity? What's the chance you have a PSA levels over 10, you have a positive test, given that you have you actually have cancer? What would be the numerator or denominator for that? So truly having cancer, right, is the 165 individuals. And what percent of them actually would be diagnosed according to this. There's other ways that the diagnosis is done, so that's would not be the only way that they would catch this or find this. And just 10, right? So the sensitivity of 0.06, right? Not too high. Generally, you'd want that sensitivity of 80, 90%, that would be excellent. But that's what it is in this case, right? What if you had instead, alternative, let's say what you called it the PSA, you're going to say, yes, I think that somebody has this, call it a positive test, if they get above 4. Right? 4, so with many tests that are quantitative in their scale, right, there's an issue of cut point. How big is a signal that there's a risk? So now if you define the test, instead of being greater than 10, but greater than 4, right? Now there's 30 individuals that are bigger than that, and that's 0.18. Does it round to that? Yeah, it rounds to 0.18. So this would look better, right, in terms of this measure of sensitivity. The other thing that gets reported, though, is the chance of making a wrong decision about the people that don't have cancer, right? Because if greater than 10, here's 10 people who did not have cancer but had high levels. Here's 60 people that had levels in this range and they don't have cancer, right? So the other term that's used is called specificity. This is the probability that you have a negative test given that you're truly negative, which means no cancer in this case. We've considered two different tests, right? If a test positive means PSA greater than 10, then a test negative would mean the PSA is less than or equal to 10. So what's the probability that the PSA is less than or equal to 10 among those who have no cancer? So from this table, there were 835 with no cancer. Going back one page. So there's 835 with no cancer. With that strict test that say PSA has to be about among 10 to be called a diagnosis. There's 825 there we go. Next page. There are 825 who would not, have a positive result. The signal that maybe there's something wrong if we allow, if we require 10 or above. So in this case, the specificity is, for this one, is about 99%. Among those without cancer, having that strict thing above 10 very, very rarely would ever call anybody into question. How about this other test? Test positive now means PSA greater than 4. And then a negative test has to be, test positive, has to be the PSA less than 4. What's the probability that we get a positive result, a negative result, given that there's no cancer? There'd still be 835 in that column. But how many people now get a negative diagnosis, that they have a lower PSA? So if we move the cut point for the test lower, Now our probability is 765 out of that for the sensitivity. So 765. This one is 92. Sorry, specificity, 92%. We would like to have this higher, so we're looking at specificity. The strict test makes sense because we don't make this error for the people who don't have cancer. But looking at the sensitivity, getting a correct diagnosis for the people that truly have cancer. Right? This one with the PSA less than 4, the other test, right, seems to be better. And so there's this trade-off, right, in this, in its levels. There's then something called graphing these things in engineering and other things. There's something called an ROC curve. ROC stands for a receiver operator curve. And it comes out of information theory where engineers were trying to send signals across long distances, and the signals generally are sent as little bytes, zeros and ones, or short and long, and it would depend on how you send it, right? Under different technology, different schemes and things like that, different errors could be made, right? So that the information going, this coded information, could go and you could have ways that made it easier to call something a positive or a negative, and depending on that, you would get more correct differences in sensitivity specificities. And so what this curve does is it's 1 minus of specificity is put down here. And the sensitivity is put up here. Probabilities, the conditional probabilities. And the place you really want to be is right up here. Right? You want specificity nearly 1 and sensitivity nearly 1. Here's 1 and 1 and 0, 0. And like in this particular example, we had one way of doing it that got a really quite low sensitivity. Well, we got one that was kind of, we got some trade-offs here. We got one that had higher specificity, but it had lower sensitivity, so it was over here. And then another one had lower specificity, but higher sensitivity. And so, we used a PSA of 4 or 10, really, as 2 cutoff points. Right? But you could imagine doing 5 and 6 and 7 and everything there. And as you move that cutoff, you're going to get more specificity, less sensitivity. You're going to trade off in those things. Right? And so there's some boundary curve in here that our tests are going to follow on this. And this curve is called this receiver operator curve. And depending on how you choose the cutoffs for the different tests, you get things along there. Right? Now, in reality, you have to pick something. Right? What type of test are you going to do? Which of these 2 errors is worse? Would you rather call more people positive, possibly cancer, when they don't actually have it? Or would you rather call more people non-cancer when they actually do have it? There can be different costs associated with that diagnosis, and so that might affect which of these you like. So there's many different things that do these ROC curves in statistical analysis. So this is just I just Googled this, and so there's this MedCal thing, and what they have is this little manual. It talks about predictive sensitivity and specificity, and it's predictive, you get predictive values, correct or in error. And as your criterion values, like the PSA level is going, it's changing the specificity. One's going up as one's going down. And they can make a little ROC curve here, and depending on how serious the 2 different types of error are, you might choose a test along there. And, you know, this, well, get down here a little bit more, there's, like, get a little bit smaller, right? So there's some data that are at the bottom of this, so kind of a summary table. Right? They have an example where they're kind of trading off these things with different numbers and different criteria values of some test. And as this criterion is changing, sensitivity is going one way, specificity going the other way. And within medicine, they're looking at these different, the trade-off of these different things. So really it's conditional probabilities set up that we're estimating. So, so probabilities get used a lot of ways. Sometimes as odds, sometimes as odds ratios, sometimes in terms of these terms, but it's often conditional probabilities, and sometimes conditioning on another variable can change the whole situation. Once you know more information, right, it can alter those things for practical evaluation. And so in a new homework will be posted pretty soon. So we'll be doing a week where you calculate some of these different measures, look at the different ways things are transformed. Any questions? So I thought we'd do one, just a different example, kind of a problem, through things. So, called a Monty Hall problem. Anybody heard of this problem? So there's a game show in the past called Let's Make a Deal. As part of the game show, the host of the game show, Monty Hall, would show contestants 3 doors, and behind these 3 doors, doors 1, 2, and 3, one of these doors has a car behind it, or a washing machine, or some super prize. So one has a car. The other 2 have goats. Go 1 and go 2. You don't want to get just kind of a wacky game show with all this stuff. So not that people would actually take the goat home or anything, but they would, you know, the goat walking around on stage, and that was also so funny, right? And so the idea is you get to pick a door. Where do you think the prize is? What's your probability of winning when you pick a random door? 33%. Yeah, 33% probability that you win when you choose a door is just 1/3. So let's say, which one do you want to choose first? Oh, 1. Want to choose 1? So you put your mark on 1. Okay, they monitor this. So you're really happy with that door? Okay, I'm going to show you something. I'm going to open this one. Right, I'm going to open this one, and there's a little goat here. Right, there's a little goat with a tail, and something like that's a little goat or something, right? A little animal there. So there's a goat behind that one, right? Now, do you want to stay with your original door, or do you want to pick number 2 now? You're not going to pick number 3 because there's a goat there. Some people in Vermont might like a goat. You know, it's a different story. Should you stay on your original question? Stay or switch? Which one is going to give you a better chance of winning? Or does it matter? What's the probability of winning if you stay? What's the probability you stay if you switch?
If you switch, you double your odds.
If you switch, you double your odds. Why do you double your odds?
Because now you've chosen 2 doors of 3.
You've chosen 2 doors of 3, but you have your mark only goes over 2, right? So you're only on 1. But yeah.
Does it change to be that there's now like a 50% chance the car is?
Well, so that's the crux, right? Is it just out of these 2 doors, right? Or somehow do you get to count more, right? You get a 1/3 before and 2/3 again. You know, if you 2/3 you lost, but right. So it's settled. So when this was, somebody wrote one of these questions into Maryland Best Savant, like Grade magazine, right? And she gave an answer, and all these people wrote and said, oh no, you're all wrong and everything, but she was right, but, so it can be kind of confusing how you think about these things, right? So conditional probability can help us with this, right? So let's imagine a scenario, right? Kind of get some reasoning by example. Say you have a bunch of doors. Say you have doors 1, 2, 3, right, up to 1,000. And say initially you choose this one. And then Monty Hall comes along and says, there's a goat here, there's a goat here, there's a goat here, there's a goat on all of these, and there's a goat on this one. Now your choice now is to stay with the original one at door number 1, or switch to that other one. Does one of those doors look a little, give it a little preference by the way this is done now? Do you want to stay with the initial pick? Right? Or would you want to go to this one that's left over? Are they kind of equally likely, or does one get a little more probability? So the probability that it's door, right? So we can do a little chart here, right? So let's say that the location of the car is either in door 1, 2, or 3, right? And maybe with equal. And let's say we pick some door. So we pick door 1. You could repeat this with picking door 2 or picking door 3. You put a mark on one, and there's 3 doors. So it's kind of a 1/3 chance that you've won. You're winning here. Let's explore a strategy. Right? So if you put this here, so Monty Hall, right, it's in door 1. This is where the car is. That's where it is. And you pick door 1. Right? What does Monty Hall have to do? He has to open either 2 or 3. Right? He can't open 1 because that would tell you here's your car. Right? So that doesn't build any suspense. And let's say he just makes this choice equally, 1/2 or 1/2. Now, if he's picked door 1, if you pick door 1 and the car really is behind 2, he has to open, right, 3. This is the door that gets opened. And there's a probability of 1 of that. He doesn't have any other choice. Right? He can't open the one with the car, because that would kind of mess up the whole thing. He's not going to open your door. But now let's say you picked 1, you put your stamp on 1, and the car really is behind 3, and Monty Hall knows that. Right? So the only thing that can be opened is 2. Right? Now, do you want to, open 2. So the closed doors are 1 and 3, or 1 and 2, or 1 and 2, or 1 and 3. The one's closed because you put your mark on it, and the other ones are that. Yeah, that's right. So, which strategy do you want to think about first? Do you want to think about switching? Right. So if you switch, you would go to door 3. Over here, you would switch to door 2. Here, you switch to door 2. Here, you switch to door 3. In this case, if the car was really on 1, switching would lose for you, right? And this one, if you switch to door 2, that would also lose for you. If you go down this one and pick door 1, wait, car is on 2, and now you switch to door 2, this would be a winning situation. You picked 1 and it was at 3, and now you switch to 3, so this would win for you. So there's 2 wins and 2 losses and 2 wins. But are these equally likely? If we multiply things out. We multiply all the way through 1/3 and 1/2. There's kind of a 1/6 over here, and 1/3, 1/2, and 1/3. over here. This one, right, there's just a 1/3, and there's a 1/3. 1/3. Right. Over there, so you pick door 1 and then follow this logic, and your strategy is to switch, what's your probability of winning?
2/3.
Yeah, 2/3, right? 2/3 for win. If you switch. If you don't switch, if you stay the same, you're going to win in these two cases because you go a car with under 1, and you picked one. And if you stay there, you win. But there's only 1/3 probability that you'll be going down that path. These other two, if you don't switch, you don't win because you didn't pick 2 or 3 originally. So there was 2/3 over here, and so this kind of Ted was saying is that you kind of had a 2/3 chance because there was 2 doors, and he's kind of narrowed down one of those for you, and given you a little bit of extra information about one of those you didn't pick. Right? You still have 1/3 on there, and it doesn't equalize in that because that selective information about opening one of the doors, right, really affects not this first choice, but it affects these two that are over there. So you still get 1/3 for this and 2/3 for one of these two. So you get a better chance if you can narrow out some of the information there. Right? So in terms of the conditional probabilities, that you could reason about things with conditions and some of these things a little bit more formally. Yeah.
On the bottom line of reasoning,
Yeah.
if you started by picking door 3, how could you switch to door 2?
If you started picking door 1,
Oh, okay.
and so if you pick 1 and then the car is under 3, then he has to open up 2, and if you switch, you're going to switch to door 3. So you would switch to the right place in there. So all right. So it's a few topics in probability that we've done. And a new homework will come up. We'll look at a few of these things, and I guess I need to pick up the next one. Have that written up. I just should have dropped it off. Okay, sure. Sure. When's your next game?
Not till spring break.
Oh, not that one.
Thank you.
Yep. Thank you. Oh, that's your signature.
It doesn't make a difference, it's just our coaches. The 29th. Thank you.
Sure. Good, thank you.